Good morning to all of you. So in the last class we had started the topic of shearing force in the bending moment diagram and discussed how to draw the shear force diagram, how to calculate, how to draw the shear force and the bending moment along with their diagrams for a cantilever for various types of loads. Now we are going to discuss these diagrams for a beam, and we have discussed what is a beam, what types of beams do we have, do we come across in our daily life. So first of all we have a simply supported beam. Beam is simply supported at its two ends and it is having a point load W at any point at its span. Total length of the beam is L, which is equal to A plus B. The load is located at distance A from end A and at distance B from end B. This is the arrangement. For this you have to draw the shear force and the bending moment diagram. Now as per our general practice, what we do is we take a section and the section is between these two loads. So this section we have taken, this is at a distance x, cross section at a distance x from this load, and now we have to find the shear force and the bending moment at this section between the loads. And first of all let us find it between these 2 points, between this reaction here. Suppose the reaction is R1 and here it is R2. So first of all we have to find these reactions, and this we can do by using the principle of equilibrium. Net force on a body in x direction is 0, in y direction is 0, and net force in any direction, net moment, is also 0 at any point in a body. These are the conditions of equilibrium. Now there is no load in x direction, this is x and this is y direction, so there is no load in x direction. So net force in y direction must be 0, so net downward force W must be equal to net upward force R1 plus R2. Now what we can do is, according to the third condition, to find the values of R1 and R2, let us take the moment about any point. So you can take the moment about point A, B, and let this point be C where the load is acting. So if I take moment about C equal to 0, this gives us moment of A about this is in clockwise direction, whereas B is having anti-clockwise movement. So moment of R1 about A is R1 into A, and that of R2 is minus R2 into B is 0. So R1 is B R2 by A, and use this equation. W is putting the value of R1 here. So this gives us R2 is WA divided by A plus B, which is WA by L, and we can also write similarly R1 is WB divided by L. These are the reactions which we have found. So let us draw them. So for x between, this x is lying between 0, here x is 0, here x is equal to A. For this condition, what is the shear force? At cross section at a distance x, the shear force is the force on this side of the section, which is R1, and it is positive as per our sign convention. So this is equal to WB divided by L, or WB by A plus. So it is a constant value. So the shear force from this point to this point, it is constant WB by L having a positive. Is WB divided by L with a positive sign. Now what happens when we take the section between the load W and RB? So let us move this section here, and now the distance is measured. This distance is x. Now forget this previous calculation. So we have the load on this side of this is R1 in upward direction and W is in downward direction. So for x between A to B, the shear force is, now nature of this load is positive as per our convention, and this load is negative. So R1 minus W, by putting the WB by L minus W. So Fx here is minus WA divided by L. So you can see that the shear force for this portion is negative because this load is more than this reaction. Obviously it will be. So here the shear force becomes negative, it comes down, and this is minus WA divided by L. It is constant for the entire section. Here where a point load is acting. So at the point C, the change in shear force is equal to, we have positive WB by L minus of WA by L. You will find that this is equal to W. So whenever we have a point load at any point acting, there is a change in the shear force, and that change is equal to the magnitude of the point load. So shear force changes from positive to negative, and this change is equal to this point load acting here. Now the shear force on this end at end A is equal to the reaction we have found. This is equal to this reaction R1, and here at this point it is equal to this reaction R2. Now let us draw the bending moment diagram. This is the shear force diagram. Now the BMD. And you know that in BMD we have to take the moments of these shear forces about this section. Now for x varying between 0 to A, the bending moment is moment of this reaction R1 here about this section, it will be in this direction, clockwise direction. So this is equal to, now this will be positive, the moment of this type of load will be positive and it is sagging moment. So R1 into X, R1 is WB by L into X. So this is a straight line, Y is equal to M into X, positive. So at X equal to 0, bending moment is 0, and at X equal to A, bending moment is WAB divided by L. So here it is 0, this is a straight line, and the bending moment here is WAB divided by L. This will be its maximum value. Now for this side, this obviously will be a straight line. We can join this. You can calculate from this side also, or you can find from this side. Both ways you can do. Now if I write for section between x equal to A to B, we have mx is moment of this load which is positive, R1x, R1 is WB by L into X minus moment of W about this section, it is negative bending moment. So minus W into distance from this to this is X minus A. Now one thing you have to keep in your mind if you use this calculation, that when X is less than A for this part, this term W into X minus A is immaterial. This will be 0 if X is less than A. This will be used only if X is greater than A. At X equal to A, this term is 0, so bending moment is WAB divided by L. So X equal to A, mx is WAB divided by L. And as I told you, this term is used only if x is greater than a. So at x is equal to a plus b, or which is equal to L, the bending moment is W b divided by L into x is L minus W x minus a is b, that is equal to 0. You can draw it like this. The bending moment is 0. So at the two ends, simply support it, you can see bending moment is 0, and we have shear force is equal to the reaction at the two ends. So this is how you can draw the bending moment diagram. As I told you that if you draw it from this side, the bending moment of this will be positive, and here bending moment will be 0. If I draw it from this side, that is, I take the section from the other side at a distance x, this is the cross section for this part, this remaining part, then the bending moment will be, let this be equal to x dash. I will show it here. Mx dash is equal to R2 multiplied by x dash. So that is W a by L into x dash. So at x dash equal to 0, mx dash is 0, putting x dash equal to 0, and at x dash equal to this distance is b, the bending moment mx dash is WAB divided by L. So it is also a straight line. So this is how you can draw the bending moment diagram and shear force diagram for a beam. Now suppose for this beam A and B both are equal to L by 2. That is, the load is acting at the center of the beam. So we can easily write for this beam in that case A equal to B equal to L by 2. The load is acting at the center. The reactions for this symmetric type of loading, R1 equal to R2 equal to W by 2 by using the two equations, and you can draw the shear force and the bending moment diagram. So it will be equal to R1 for this portion. If you compare with this, if you write B equal to L by 2, so this is W by 2, which is equal to R1, and here there is a change in shear force which is equal to W. So here this is W by 2, which is equal to R2. This is minus, this is plus. This is the bending shear force diagram. And about the bending moment diagram, the bending moment diagram, M maximum is always at the point where the maximum load is acting. Here it is only at one point, which is equal to WAB by L. If you put A equal to B equal to L by 2, so this is WL by 4 at the point where the load is acting. This is the case when the symmetric loading is applied on the beam. So this was the case of a simply supported beam having the point load acting at any point on its span. Let us now next discuss the case of a beam which is having the uniformly distributed load along its span of uniform intensity.